Hi everybody. This is really the first lecture where we use Lagrangian methods to solve for the acceleration of objects. So the examples I'm going to do are the harmonic oscillator and the simple pendulum. Pretty simple examples, but then we'll get a little bit more complex and I'll show you what we do when we have 2 or 3-dimensional problems. So that's what this lecture is. Okay, so one of the reasons that the Lagrangian method is useful is that we don't really have to know anything about the forces. We need to know about the energy, because if you remember the Lagrangian, let's say x is our dependent variable, time is our independent variable, and the Lagrangian is the kinetic energy minus the potential energy. So it's not the total energy, it's the difference between the kinetic energy and the potential energy. And our Lagrangian equation was this. I think this is the way I wrote it down. Or in this case it could be x, but it should be 0. So since this side is 0, we could also multiply both sides by negative, and you'll see it written a lot of times like this. Let me use x instead of y here. Okay, so what we do is we try to identify the kinetic energy, potential energy for our system. We write down the Lagrangian and then Lagrange's equation and see if we can solve for the acceleration. So let's look at the harmonic oscillator, the canonical problem. Have a mass attached to a spring constant K. Is stretched from its equilibrium point by a distance x. And let's try to find the acceleration for this. So we identify the kinetic energy, 1/2 mass times the velocity it's moving, which is x dot squared. It's the kinetic energy. Potential energy, it's a stretched spring, 1/2 kx squared. And then we're going to find the equation of motion here. So first L is 1/2 m x dot squared minus 1/2 kx squared. So the partial of L with respect to x is simply going to be negative kx. We take the derivative with respect to x. The partial of L with respect to x dot is mx dot. And then if I take the time derivative of that, it's going to give me mx double dot. I'm assuming the mass is not changing. So then the equation of motion is this. There we go. And I can solve for the acceleration equals so again, this is useful. I don't have to know that the force is negative kx. I just solve for this equation of motion and I get that. Okay, let's look at the simple pendulum. So I have a pendulum on a light string, the mass m down here, string length L. So if it went straight down, make some arc length. This is an angle theta. This is an arc length S equals L theta. That's right there. So let's find the kinetic energy. It travels along this arc length. Let's say it's going this direction. This time, 1/2 its mass times s dot squared. But we could also write that as 1/2 m L squared theta dot squared. Potential energy, it's up a certain height, this distance here. I'll call it h. So mgh is this potential energy, and that's mg L minus L cosine theta. That's that height, because right there goes straight across, that's L cosine theta. All the way down is L minus L cosine theta is little h. So mgl 1 minus cosine theta. So the Lagrangian, and I'll write the Lagrangian in terms of theta dot d equals 1/2 m L squared theta dot squared minus mg L 1 minus cosine of theta. I want to set up Lagrange's equation. So dl d theta is going to be negative mgl, and then when I take the derivative of cosine of theta, I get the negative sine theta. That's why I get that negative. So I'll get the derivative with respect to theta dot is just ml squared theta dot, because that 2 comes down, cancels out that 1/2. And then if I take the derivative with respect to time of that, it's ml doesn't change, theta double dot. So I get my equation of motion, ml squared theta double dot minus negative mgl sine theta, so plus mgl sine theta. And again, now if I solve for theta double dot, so this whole thing has to be 0. Solve for theta double dot, I get negative g over L sine theta. And of course, if we do the small angle approximation, we would get theta double dot is negative g L theta, where sine theta is approximately theta. There we go. Example 2. So now what we want to do is, let's talk about a little bit of a harder problem, and one that involves 2 dimensions instead of just 1. So if we have a Lagrangian that's a function of x, y, and z, and each of these depends on the parameter t, then in this case we would have 3 Lagrangian equations. I'll write them like this. Okay. So, for example, if we have a ball thrown through the air under the influence of gravity, so let's say it's right here right now, the force is mg downwards, x, y. So we're going to have a Lagrangian that depends on x and y. One half mass, the velocity is x dot squared plus y dot squared. That's the velocity squared, so that's the kinetic energy. Potential energy is mgy, so there we would go. Partial of L with respect to x is just 0, just like the partial of L with respect to y. Oh, that's equal to negative mg. dl dx dot is mx dot. dl dy dot is my dot. So our two equations that we get from this are, again, this. So no acceleration in the x, and this really should have been, well, that's negative up there, so that makes that plus equals 0. So then I get y double dot equals negative acceleration in the y direction. So let's do a little harder problem in 2 dimensions. So as you'll find, the Lagrangian method allows you to do some problems that are just really hard to do with the Newtonian method. So for this example, let's take a wedge. So here's my wedge, and it's sitting on a table, or a smooth table, no friction. And its position relative to one end of the table here, let's call that big X. Now on that wedge, so the wedge, let's say, has mass big M prime. But on the wedge, there's another mass, little m, and its position relative to the top of the wedge, let's call that little x. I'm going to call this big X prime. The wedge is at an angle theta with respect to the horizontal. Okay. So there's 2 degrees of freedom for this problem, and we're going to have to use 2 dimensions. So our coordinates are big X prime and little x. So let's find the kinetic energy. The kinetic energy, total kinetic energy, is going to be for the big wedge. And the little mass. And we got to figure out the velocity for that little mass. I'm going to call it v squared for a second, but let's figure out what v is now. The big wedge is moving with that velocity, and then we have the little wedge moving, little x. So this resultant vector is v. And this angle is theta. I need this angle here. I'm going to call it alpha. Because then I'll use the law of cosine. So what is alpha? Well, alpha is 180 minus theta. So okay. So v, using the law of cosines, v squared is big X dot squared plus little x squared minus 2 times big X dot little x dot cosine of alpha. And the cosine of 180 minus theta is going to be just cosine of theta. You can look that up if you don't believe me. So we have that plus little x squared. Oh, it's cosine, let's see, 180 minus theta is going to be negative cosine of theta. So I'm going to get a plus here, too. So there's my velocity. The potential energy. For this block, it's up here. It's just going to be what am I going to do for that? Let's say, I get to say where it's 0, so I'm going to say it's 0 right up here. So negative little m g x cosine of theta. No, I'm sorry. That would be sine of theta. Okay. So L is equal to 1/2 big M big X prime dot squared plus 1/2 M and then I have this big X dot squared plus little x dot squared plus 2 big X dot little x dot cosine theta minus mgx sine theta minus minus, so that's plus mg little x sine theta, if I didn't make any mistakes. So now we're going to have two Lagrangian equations. Let's put that up here. Just don't quite get rid of that. So let's find dl d little x. Do we have that anywhere? Yes, we do. We have that derivative right here. It's mg sine theta. And then we have dl d little x dot, and that's going to be m x dot plus that 2 will cancel out that 2. I'll have an m here. I'll have a big x dot and cosine of theta. So my equation, first equation I have, is equal to mx double dot plus m big X double dot cosine theta minus dl dx equals 0. Okay, and then, so that's one equation. Then I'm going to have dl d big X, and that's just 0. And then I have dl d big X dot, and that is equal to big M. If you look up there, what else? Big M, big X dot, plus I have a little m, big X dot, plus m little x dot cosine theta. So d dt partial of L with respect to big X dot minus dl d big X, saying that to 0, but that's going to be equal to big M prime big X double dot minus or plus little m big X double dot plus m little x double dot cosine theta equals 0. So I have these two equations. Now I'll let you solve for little x double dot and big X double dot. So you should pause it and try it and see what you get, and I'm going to write down the solution for you. That's what I got. Okay, so there's a little bit more involved problem. So, and I think this problem would be pretty hard using Newtonian mechanics. It's a lot easier using Lagrangian mechanics. So, in the next lecture, we'll do some more examples.